With word problems, we want to search for those values that are going to give us numbers for the initial value and the growth or decay factor, and also wording that helps us determine whether our function is growing or decaying. So we're trying to fit this function form f of x equals a times b to the power of x, where a is the initial value and b is our growth factor. And part of calculating b is coming from this 1 plus or minus r, where r is this growth or decay rate. So let's see how these come together. This first example, India is the second most populous country in the world, with a population in 2008 of about 1.14 billion people. The population is growing by about 1.34% each year. Write an exponential function for India's population and use it to predict the population in 2020. Okay, and this is population growth. So what that tells me is that when we find a value for b, it should be over 1. Because 1 is the idea of 100%. So if something's growing, it should have 100% plus some extra stuff. If we have exponential decay, what we should see is a number between 0 and 1, because we're taking some percentage away from 100%. All right, so we have this relationship of 2008 and 1.14 billion people. Now, they don't tell us how to define our variables, and what we can do is define it in a way that'll make the work quite easy for us. So what I'm going to do is describe x as the amount of time that's passed. So x is going to be year, but instead of dealing like with x equals 2008, which is fine, is just going to get messy, what would be really nice is just have 2008 represent kind of the start of time for us. So what I'm going to do is call x years after 2008. So then what that will do is that when I use x equals 0, that'll be the equivalent of the year 2008. So what that means is I know that when we're in 2008, there's 1.14 billion people. So I have this coordinate 0, comma, and then I'm just going to shorten it to a 1.14 for ease, so I don't have to deal with all those zeros. So by setting x in that way, what I just did is I let that be our initial value, so we don't need to go solving for it. Yay! All right, so we have our initial value of that 1.14, so in terms of our function, that's going to be our value for a. Then for b, what we're going to do is to calculate b, we're going to use 1 and then plus, since it's exponential growth, and this 1.34%, that's our value for r. And when we're doing calculations, we want to take percentages and change it to the decimal form. So I want to use 0.0134. So b is going to be equal to a 1 plus 0.0134. So b is going to be 1.0134. So our function, measuring the population in terms of years after 2008, we're using an initial value 1.14 and then times 1.0134 to the power of x. All right, so there's our function, and now we want to find the population, or rather predict the population for 2020. So if we're dealing with years after 2008, we're looking for x equals 2020 minus 2008, which is 12. So we want to look at plugging in x equals 12. So f of 12 equals 1.14 times 1.0134 to the power of 12. And we would just plug that into a calculator and get 1.3374. And then just keep in mind, so that's our population, and that's in billions. So in, let's say the predicted population for 2020 it doesn't make much sense because 2020 is past now, but the predicted population for 2020 was I'm going to go ahead and round that to 2 decimal places, 34 billion people. Okay. All right, this next question. A population of 1,000 is decreasing 3% each year. Find the population in 30 years. All right, so that 1,000 is our initial value, so we're going to be using A equals 1,000. Then for B, we would be taking 1, and then we would do minus because it's decreasing. And then our rate is that 3% or a 0.03. So for B, we're calculating 1 minus 0.03, which is a 0.97. So again, we haven't really looked at decay yet, but the idea is, so 100% is the whole. So if I want to take away 3%, really I'm taking 97% of what I have. So our function, let's say f of x is going to be equal to 1,000 times 0.97 to the power of x. And then we're looking at 30 years passing. So what we want to do is look at f of 30, which is 1,000 times 0.97 to the power of 30, and that should be 401. So the population in 30 years would be 401. We don't say it's people, so I'm just going to leave it at that. I was going to say something. Oh, yeah. It's good to have our sentence at the end to see if it makes sense. Like with these, make sure you go back and read the question again. It's like we started with 1,000. We're only decreasing by a tiny bit each year. So with 30 years passing, it makes sense that we started at 1,000 and decreased down to 401. So it's good to take a moment to double check, like, did that number in fact go down? Because it should be. Or like that last example with India, the fact that it was growing by a tiny bit each year. So we started at 1.14 and then 12 years later had 1.34. That makes sense. So just be sure to put it back into context to see how it works. Okay, our last application here. So we have in 2002, a company had 80 retail stores. And by 2008, the company had grown to 180 retail stores. If the company is growing exponentially, find a formula for the function. So what we have here are 2 cases. We have basically 2 coordinates. So first, let's define our variables. X is going to be the amount of time that's passed. So let's call it years after 2002. And since we can define it, that makes it nice because then our units for 2002 and 80 would be 0, 80. That would be our coordinate. And then what we'd have is 6 years later in 2008. So 6, comma, and then 180 retail stores. So we have these 2 coordinates, the initial values coming from that value of 80. So we're going to have A equals 80, but we don't know what B is. Notice they didn't mention anything about a percentage. So if I'm trying to fit my A times B to the power of X, I have A is equal to 80. I don't know what B is. I have some exponent of X. What we want to do is solve for B by plugging in that second coordinate. So I want to plug in that 6, 180. So let's see, output of 180 equals 80 times B to the power of 6. We're going to divide both sides by 80, which is a 2.25. And then we're going to use a rule that comes from exponents. So I have this B to the power of 6. And what I want to do is I want to make that an exponent of 1. I want to get B out of there. I want to get it out of the base. So what I would want to do is I have B to the 6th. Sorry, I know my B's and 6's look very similar to each other. B and power of 6. So if you have b squared, the idea would be that you take the square root of both sides. If you had b cubed, you'd be taking the cube root. So it's the same idea here. It's like we're taking the 6th root and showing that as a rational exponent. I'll write that off to the side here because that's what we're using. Rational exponent basically means an exponent with a fraction. So if you have x to the 1/2 power, that's the same thing as the square root of x. If you have x to the 1/3 power, that's the same thing as the 3rd root of x, cube root. So if I have b to the 6th, if I want to take the 6th root, then what I'm doing is I'm going to put parentheses around b to the power of 6, and I want to raise it to an exponent of 1/6. Because what's going to happen is my power to a power rule, you multiply those together, and 6 times 1/6 is 1, which is exactly what we want. Whatever we do to one side of the equation, we have to do to the other. So I'm going to take that 2.25 and raise it to a power of 1/6. So we plug that into a calculator, and that's going to give us b equals 1.1447. With these, and especially, I guess with this one, we're not going to be plugging in values, but keep b accurate to at least 4 decimal places. If we do any sort of rounding here, it can really change answers. So at least 4 decimal places there for our value of b. So that tells me my function is going to be 80 times 1.1447 to the power of x. Let's see, 1.1447 tells me that our, number of stores is growing, which we absolutely saw. We went from 80 to 180. So having something over 1 makes sense. So it's good to just throw it into context a bit to make sure it's all connecting.